Hi there, welcome to your lesson on kinematics, a great application of calculus. What is kinematics? Kinematics is the study of the movement of objects. A particle moving in a straight line is an example of the simplest type of motion, and that's what we'll deal with in our lesson here. We won't do anything more complex than linear motion. To describe simple linear motion, you need a starting point, a direction, and a distance. So a path is the set of points along which an object travels. The distance traveled by an object is the total length of the path followed by the object after it leaves its starting point. The displacement of an object is the difference between the object's position and a fixed point. This fixed point is sometimes called the origin, and is not necessarily the same as the object's starting point, and we'll talk about that in just a second. So there's a big difference between distance and displacement, and I'll show that in a moment as well. For example, if you run a complete lap around a standard athletics track, the distance you will travel is 400 meters. However, after you have completed the lap, your displacement will be 0 meters, since your initial and end positions are the same. So that's a good example to show the difference between distance and displacement. Distance is the total distance an object moves, whereas displacement is how far it is from its starting point. Alright, so let's take a look at that in a diagram as well. So here is the path of an object represented by this curve here, this purple curve. It began here at point A, it went like this, and it ended here. So this part, this purple curve, is your distance. If you added up that entire distance traveled there, that would be your distance traveled. However, the actual beginning and end of the journey are measured by this straight line, and that is our displacement. And in this case, we can say it's a positive displacement. Displacement has a direction. You can say something has been displaced positively or displaced negatively, depending on that location based on a comparison to its original point. So in this case, if it went the other direction, we could say it has a negative displacement. Okay, let's begin with this example just to get the idea of kinematics and all its components into our minds. So let's say you throw a ball. Its height or position are dependent on time, and it is graphed here. Okay, so here's the height and here's the time, and you can see the ball goes up and then down. So its height increases and then decreases. So let's say in this case, going up is positive distance or displacement, and going down is negative displacement. Okay, let's answer some questions. Oh, by the way, the function is given here. It's a quadratic, we can see, which matches this graph. And often the position function, the function that tells us where an object is written as s of t. Okay, s of t, t being time. So at what time is the ball at its highest? Look at the graph. Okay, you can see on the graph here the ball is at its highest here at time equals 3. How high? How high is the ball at this point? Okay, 9. Whatever unit this is, we don't know. Maybe it's meters, maybe it's centimeters. Anyway, it's 9 at a unit 9 here. When does the ball have the highest velocity or speed? Okay, think about that for a second. So highest velocity and speed will be at time equals 0 and time equals 6, because the moment it leaves, it's thrown, let's pretend this is thrown by somebody, the moment it's leaving the hand, it has its highest velocity. And as it's going up, gravity is working against it and its velocity is slowing down. And then its velocity is speeding up as it's falling until it hits the ground. At that moment, it has its highest velocity again. So there's the two times. Number 4, what is happening to velocity as the ball goes up to its highest point? Okay, velocity is decreasing. Again, it has its highest velocity, but then it's slowing down. So the speed of the ball is decreasing. When does the ball have no velocity? This is a strange thing to think about, but when it reaches its highest point, there's that single moment in time when its velocity has decreased so much there's no velocity, and that's why it's not rising anymore. At that moment it changes direction. That means it has no velocity, and then gravity overtakes it completely, and now it's falling, so its velocity is in the negative direction. Velocity, like displacement, has positive and negative values. So this would be positive velocity, this would be negative velocity. Okay, what is happening to velocity when the ball is falling from its highest point? Okay, the velocity is increasing. Okay, even though the velocity is becoming a bigger negative velocity, it is still increasing, right? It's speeding up. And that's an important point that we're going to look at a little bit more later as well. Okay, so considering 1 to 6 above, do you see a connection between velocity and some aspect of the graph? So again, look at the graph. Is there a connection between velocity and something you see on the graph? Well, that connection should be clear, I hope. The velocity is the slope, right? Velocity is the slope. We know it is like the speed or the slope of the graph, which means we're looking for tangent lines. So if we can find a velocity by thinking about tangent lines, then we can find velocity by taking the derivative of this. Because when we take the derivative of the position function, we'll get the velocity function, which shows the slopes at every point, which is the speed at every point, right? But before we do that, let's draw a motion diagram from time equals 0 to 5. Motion diagram is just that linear path that shows what's happening. So we can show at time 0, and then it's moving in one direction. So in this case, it's going up. So it has motion in one direction. And then at time 3, it changes its direction. We show it like that, and it's moving in another direction. Now, the lengths of these are important. This is shorter here because at time 5, it arrives here. Okay, we just didn't ask you to show what happens until time 6, which would be, if it was time 6, it would go all the way to here because it's at the same place. But at time equals 5, it's here. It hasn't reached its starting place yet. So we have this simple diagram. All right, number 9. Find the change in displacement. Okay, now let's go back to what those words displacement and distance mean. Displacement, again, means how much has it changed in relation to its starting point. Okay, so considering that, it went up 9 units, down 9 units, and it ended up here. So its displacement, or the end result is like it hasn't moved at all. That's the displacement. Its position at the end is the same as its position at the beginning. Okay, find the total distance traveled. Now the path matters. Now we say it went up 9 and down 9, so its total distance traveled is 18. So again, that's highlighting the difference between displacement and distance. Alright, so now let's jump back to what I was saying. When we have a position function, to find the velocity function, all we do is take the derivative of the position function, because that will give us the slope at every point, and the slope tells us the velocity. So the velocity function in this case is negative 2t plus 6. That's just the derivative of that. Okay, so let's fill in the table here to figure out what are the velocities of the ball at every point. So at time 0, the velocity is 6. We put 0 in here, we got 6. Okay, at time 1, the velocity is 4. How about at time 2? It's 2. Okay, fill in the rest of the table. Okay, look what's happening with velocity. Has a high positive velocity. We know at the moment it left its hand, we talked about that, it had a high velocity, and then gravity is acting on it, so velocity is slowing down, but it's still positive velocity because it's still pushing the ball upwards. And then at time 0, the point where it changes direction from going up to falling, no velocity, we can see that here. And then negative velocity. Velocity has a direction, and we say negative velocity because now there's increasing velocity, but in a different direction, downwards. Okay, so what about acceleration? Acceleration is the derivative of velocity. So it is the double derivative of the position function, right? We go from position to velocity, then acceleration. So here's our velocity function. What is the acceleration function? Okay, acceleration is the derivative of velocity, therefore negative 2. Okay, what this tells us is the ball always has a negative 2 acceleration. So every second, velocity changes by negative 2. That's what that means. And look at the table we made for velocity. You can see the acceleration in the table clearly. It had a velocity of 6, then 4, then 2, then 0. The velocity is changing by negative 2 every time. And after you pass 0, negative 2, negative 4, still changing by negative 2. So all the way along the velocity is negative 2. Okay, so let's see that. Let's draw our velocity graph on here. You have this function. You should be able to graph a linear function. Let's draw it. Okay, and our acceleration. So velocity, it has a y-intercept of 6 and a slope of negative 2. So here's that line. And then acceleration is this equation, negative 2. So it's just a horizontal line at negative 2. Okay, let's talk about these together. So here is the path followed by the ball. Here is that velocity that we showed. There's always that negative velocity. It's always decreasing, okay? Sorry, always a positive velocity, but decreasing, right? So positive 6 to start, then a lower velocity, lower, lower, lower. Here it has a 0 velocity, and you can see here velocity is 0, and then negative velocity values here. And acceleration, always negative 2. And here's an important thing to note. Here the ball was slowing down because it had a positive velocity, but a negative acceleration. So it's slowing down. And here, after here, it has a negative velocity. We can see that here. And a negative acceleration. So we can say it's speeding up. That's important to note. Even though the acceleration is negative here, the ball is speeding up because the velocity is also negative. So comparing velocity and acceleration is an important thing we're going to have to do with these. All right, here's another example. Here's a position function, and it represents something. We don't know what's going on yet, but we see a position function and we see the graph. First question, what would the derivative of this function represent? On this graph here, what would the derivative represent? Well, it would be the slope of the graph, right? And maybe you already said velocity because we already talked about derivative being velocity, but it's the slope, right? The slope. Now, if you're told in context that this s of t function represents the distance of a diver above the water, so imagine this is water surface here. This is their height above the water, so they jump up and then down and they make a dive and then hit the water surface here, and then they're underwater, right? Negative values. So distance above the water based on time after jump. What does the derivative represent now? Well, now we can go a step further and say, okay, derivative is the slope, which we said here. It's the rise and run figure. So it's a change in distance over a change in time. Okay, change in distance over change in time. Therefore, it is our rate or velocity. Okay, so we're just bringing this more to life here, the idea of velocity. Okay, so there's a graph. Let's answer some questions. So diver jumps. There's the function we're given. Find the average velocity of the diver during the dive. What's the average velocity? Now to find average, this is important to note as well. To find an average velocity, we do it like this. We connect the point we want to begin at and the point we want to end at. So let's say the diver begins here, ends here, and an average is just the straight line connecting those two. So the average velocity would be the straight line there. Okay, so how do we find that average? Well, we can just find the slope of that. We need the coordinates of that point and that point. Do we know the coordinates? Well, let's check it out. First of all, I set this equal to 0 because we want to know when this graph intersects the axis here. When I set it equals 0, we can use maybe our poly simulation app or graphing and checking the intersection point or the 0, and we get t equals 2.01. So I want you to note that. In the beginning it looks like this is exactly 2, but we need to be precise at it. We need to know precisely what that is, and you can see it's a little bit beyond 2, and we find out when we solve the quadratic that it's 2.01, and that's important. So now let's find the slope, because average velocity is just the slope of the position function. Okay, so slope we know is y2 minus y1 over x2 minus x1. So the points are, okay, so the y2 value, the value of y here, is s into the position function. We put the time equals 2.01, and we already know that's going to be 0. And then position at time 0 would be this position here, s of 0. S of 0 would just be, well, whatever that is, what happens when you put 0 into this function. That would be your y value there. And on the bottom here we have x2 minus x1. So we have time 2.01 minus time 0 at the beginning here. So there's our slope, and there's the answer there. So this tells us that on average the velocity is negative 4.97. That makes sense because here we have a positive velocity, here we have 0 velocity, and after that we have just increasing negative velocity. Alright, it's going to be a bigger speed, but a negative in a negative direction, therefore negative velocity. And all these negative velocity values over the average cancel away the positive ones, and we get an average of a negative 4.97 velocity. Okay, now let's find the, let's see, what does it say here? Okay, find the velocity of the diver at the instant they hit the water. Now when we say instant, we know we're talking about derivative. The very instant they hit the water, we need to know the slope of the tangent. So find the tangent, so find the derivative, and then find out the speed, the tangent value, or the slope right at that moment. So we're going to take the derivative and into it we're going to put that time 2.01, and we found the speed. And that makes sense. Look at that huge negative velocity right at that moment it hits. Here's an answer for C. Take a look at that. And here's your answer for D.